Okay, let us continue where we left. Okay, so before the break, we took the hard max margin classifier and we made things a little bit softer, right? Like by adding this epsilon, right? So, and we have this softer version of max margin classifier, right? Like with soft margins. Now, I also mentioned that C, the cost parameter, kind of tells us like how much importance we give for the violations. Like, so if there are too many violations, then like depending on how strong is your C, you're going to penalize the model that much, right? Like, so if you have like a very big C, then you don't want too many misclassifications. If you put C to be infinity, then you don't want any misclassification, right? So now this second term, summation epsilon n, kind of gives you an upper bound on the number of misclassified data points. Okay, so why is it the case? Like for every misclassified data point, epsilon n is greater than 1. So whatever the second term summation is, it tells us the maximum possible mistakes that the system can do. And you are trying to minimize this maximum possible mistakes. So I think someone was mentioning in the beginning, we can try to minimize the misclassification, data number of misclassification, right? Like, so we are kind of doing that here, but in a soft way. That's why we are, instead of trying to minimize the misclassification, we're trying to minimize the upper bound of the misclassification. Is that clear? Now, we can repeat the same primal dual process here. This time we're going to do it much faster because we have gone through the process once. So here is the primal problem for the soft margin classifier, soft max margin classifier, okay? So it's R min, W, B. Now we also have epsilons, like instead of just WB. So we have C times summation over n is equal to 1 to capital N epsilon n plus 1 over 2 W squared, okay? Subject to a bunch of constraints. The constraints are T of n, y of x n greater than or equal. This was the only constraint for the hard problem, right? Like hard margin problem. Now I'm just going to put minus epsilon n here, right? And say epsilon n should be greater than or equal to 0 for n is equal to 1. Is it clear? Simple. This is my primal problem. Okay. Now, if you want to solve this primal problem, you can solve it by using solvers. You are going to get WB and epsilon easily. Okay. Now, as I mentioned before, like we can also do the Lagrangian formulation and solve the dual problem. So there were a couple of questions in the break which are worth mentioning. So, like there was this question: why should we care about the dual problem at all? Like because we will always have more examples than the number of parameters, but that is not true. So with the recent deep learning wave, like we talk about big data and lots of data, okay, but there are still a lot of practical problems where you have small data and you have to train complex models with small data. Okay, so there is value in the dual version, and there is also another important value in like going to the dual version. Okay, with the dual version, as I mentioned before, we can make the model nonlinear by changing the kernels, right? However, like making things nonlinear in the primal version is a bit difficult because then you have nonlinear constraints and the optimization becomes much harder. So there are a couple of reasons why duality helps us. Okay, so now let's do the Lagrangian formulation. So L of W, B, epsilon. Now I need a Lagrangian multiplier for every inequality. So I have two types of inequalities here. So I have the first inequality for which I'm going to use A as usual. And I have my second set of inequalities. I'm going to use mu for that. Okay. So this is going to be 1 over W squared plus C times summation over n is equal to 1 to capital N epsilon n. Okay. Now I bring the first inequality to the objective function. So minus summation over n is equal to 1 to capital N. An multiplied by T of n W transpose P of Xn plus B minus 1 plus epsilon n. I brought 1 minus epsilon n to the left hand side. Okay. Similarly, minus summation over n is equal to 1 to capital N mu n epsilon. Is it clear? Where a n greater than or equal to 0 and mu n greater than or equal to 0 are Lagrangian multipliers. Is that clear? Now, even for this Lagrangian multiplier, right? So they should satisfy the KKT conditions. So let me just write the conditions. I'll copy this. I'll paste it here. So we have two sets of KKT conditions, like one for AN. So for AN, the conditions are something that we have already seen, right? So AN should be greater than or equal to 0. And T of n, y of xn, minus 1 plus epsilon n should be greater than or equal to 0. And the third constraint is only either of them can be active. So A of n multiplied by the second one is equal to 0. So this is for A. Similarly, we have conditions for mu. So mu of n is greater than or equal to 0. Epsilon n is greater than or equal to 0. And mu of n epsilon n is equal to 0. Is that clear? Okay. So now let us take this particular thing. We just need to solve this with respect to WB epsilon. Then we have a function of A and mu, right? That is our dual problem. So let me again copy paste this to a new page so that we do the differentiation. So I put it here. Okay. First, dou L by dou W is equal to 0. Okay. Now, is there any difference from the previous problem with respect to W? It looks exactly same, right? So like I have just added a bunch of epsilons here. So W did not change. So I don't need to do this again, but I'll do it quickly. So W minus summation over n is equal to 1 to capital N A n T of n P of xn is equal to 0. So W is equal to summation over n is equal to 1 to capital N A of n T of n P of x of n. Okay, so let us just call this as my equation 6. This is my equation 7 because we are going to substitute all these things to equation 6. Okay. Now, similarly, again, there is no change with B. So dou L by dou B is equal to 0 implies summation over n is equal to 1 to capital N, A n T of n is equal to 0. This is also something that we have seen already in the previous version, right? So the only new thing here is dou L by dou E epsilon is equal to 0. So where do you see epsilon here? Let us just consider just one n. Okay. So what are all the places where you see epsilon? How many places do you see epsilon first of all? It's a simple question. So how many places do you see epsilon in equation 6? It should not take this much time. Okay, there are answers in chat. 3, right? So there is one epsilon here, one epsilon here, one epsilon here. So when I differentiate this term with respect to epsilon, you get a C. You differentiate this term with respect to epsilon, you get minus AN. You differentiate this term with respect to epsilon, you get minus mu n. So, right? It's very simple. So it's just C minus AN minus mu n is equal to 0. Or AN is equal to C minus mu n. Let us just call this as equation 9. Okay. Now I'm going to substitute 7, 8, 9 in 6. Okay. Now, if I substitute things here, okay, and also apply the KKT condition. Okay, so for example, by KKT condition, mu n multiplied by En is always 0, right? This term disappears. So you will do all these optimization. Like I'm going to directly write the equation. It's very simple. So L of A is equal to summation n is equal to 1 to capital N AN minus 1 over 2 summation n is equal to 1 to capital N summation m is equal to 1 to capital N AN AM TN TM kernel of xn xn. Okay. Now, which is exactly same as the previous algorithm's dual, right? However, only the constraints are going to be different. So the constraints we are going to have here are an greater than or equal to 0 and mu n greater than or equal to 0. Okay. And there is another constraint which is an is less than or equal to c. So this constraint comes from here. So look at this equation. So an is positive, mu n is also positive, right? Which means an should be less than c. Okay. Or in other words, we have kind of box constraint for a. Okay. I'm going to write the dual problem directly. So the dual problem is maximize the Lagrangian formulation subject to 0 less than or equal to an less than or equal to c for n is equal to 1 to n and summation over n is equal to 1 to capital A and P of n is equal to 0. So this is my dual problem. Is that clear? So now depending on which problem you think is worth solving, you can solve it. Okay. Now, when you use given that you have seen an sklearn tutorial already, and given that you are going to use sklearn and also SVM in your third assignment, so depending on the data set, sklearn I think allows you to switch from primal problem to dual problem. It has an argument to SVM where you can say, oh, use primal problem or use dual problem. So maybe when you're doing your assignment, you can just change this parameter and see how slow and fast your algorithm becomes. Okay, so like depending on what case you are in, like the other option is going to be slow. Is that clear? Okay, so finally, like, so how do we interpret the solution here, right? Like, so there are a bunch of possibilities for an. So case 1 is when an is equal to 0. So we know that when an is equal to 0, we will discard that example. Like, so it is not a support vector. So what is more interesting is case 2 when an is greater than 0. Okay. So when an is greater than 0, then by KKT condition, we know that T of n, y of xn is equal to 1 minus epsilon n. So whenever, just for the support vectors, this equation is going to be satisfied, right? Now, there are two possible conditions here. Okay, so case 2a is when an is greater than 0 and an is less than c. Okay, so then in this case, based on our previous constraint between an, cn and mu1, an, c and mu1, so mu n is going to be greater than 0. Okay, so when mu n is equal to greater than 0, so we know that as per KKT condition, epsilon n mu n is equal to 0, right? Only either of them can be positive, right? Like, so, like when you multiply both, like when one is positive, the other person has to be 0. So when mu n is greater than 0, this implies that epsilon n is equal to 0, which means whenever you satisfy this box constraint, you are in the right side because epsilon is 0. Okay. However, if you don't lie within this box, right? Okay, so case 2b, an is greater than 0, and let's say an is actually exactly equal to c. Now this lies inside the margin, okay, and this can be correctly classified if epsilon n is less than or equal to 1, and it is wrongly classified if epsilon n is greater. Is that clear? Okay. Now, so what we have seen so far, right? Like, so when people say support vector machine, it is usually the soft version. So like the hard version is just a simple max margin classifier. Well, this is also a max margin classifier, but just a softer version of it. Okay. And we will also call this as linear SVM. Okay, because we are going to see non-linear SVMs in the future. Okay, I have already told you how to do that. Like, so you just change the kernel, you get a non-linear SVM, but like we will see that in detail later. Any questions so far? Okay. So now let's talk about the error function for a softer version, like the SVM, right? So to support vector machine error function. Okay. Now, for the points that are correct in the correct side of the margin, right? Like for correct points, we know that y of n, p of n is greater than or equal to 1. And also epsilon n is equal to 0. We already know this, right? Now for the remaining points, my epsilon n is given by 1 minus y of n p of n. Right? So what SVM is trying to do is to minimize this particular value. Like you get this as close as possible to 0, right? So I can write an objective function, which we're going to call as SVM objective, okay, which is summation over n is equal to 1 to capital N ESV of y of n t of n plus lambda times w square, okay, where in this case we're going to set lambda is equal to 2c inverse, okay. Instead of having the c parameter in the left equation, I brought it to the next, the right equation by dividing everything by c. Now the ESV of y of n t of n is given by 1 minus y of n t of n with the plus sign, okay. Now this notation just means that it's a max of 0, 1 minus y of n t of n. Okay. So what does this mean? So for every data point, I'm going to compute 1 minus y of n t of n. If this is greater than 0, then it means it is a mistake. I want to reduce that mistake. Okay. So the term is going to be just this term. If it is equal to 0 or like possible for it to be less than 0, I'm not sure. If it is equal to 0 or less than 0, then you have correct classification. So you don't penalize, so you just put 0. So this function gives you an error whenever there is a misclassification. Otherwise, it gives a 0. Is that clear? Now, this particular loss function, right? So this max of 0, error, right? Like whenever there is an error, like you minimize, but whenever there is no error, you have a 0 loss. So this loss is called hinge loss. Okay. So I think now we have seen quite a few loss functions. So can someone remind me different loss functions that we have seen so far? So what are the various loss functions we have seen so far? I think people in the chat, you can just type, all of you can type. So what are the different loss functions or error functions we have seen so far? Yeah. Least square. Okay, so I'm just going to call that a squared error. Okay. Anything else? Logistic regression, right? Like so the cross entropy or negative log likelihood error that we saw in logistic regression. Okay. So this error was, you can either call it as binary cross entropy, or if you have many classes, when you have softmax, then like you just call it cross entropy or negative log likelihood, right? So now we have seen hinge loss, right? There is also the most basic error, which is misclassification, number of misclassification points. Right? So these are the different loss functions that we have seen so far. So now let's try to understand, like, and compare these loss functions and like see what kind of solutions they would arrive at, right? Like, so now here is a graph which has all the loss functions. Okay. Now, without looking at your notes, like, I want you to guess what are these loss functions. Like, so what do you think is the green loss function? It's squared error. Okay, so because it looks like a parabola, right? Like, so this is squared error. Okay, so what is the black? I think you don't see the black one. So the black one is like this. What is this black one? It's a misclassification error, because whenever something is wrong, it just gives one error. Whenever something is right, it gives zero error. Like, it's either 1 or 0. So this is the 0 or 1 loss or misclassification error. Okay. Now we have two more candidates here. So blue and red. So blue is what we have seen just now, right? Like, so you can easily guess, because after epsilon is equal to, like after the 1 point, right? In this case, like, we are considering 1 to be the place where class changes. So after 1, you can see that it is always 0, the loss. Before 1, it is a linear loss, right? So the blue thing that you are seeing is the hinge loss. Okay, and well, there's only one thing left. Like, so the red thing that you see, which slowly goes down smoothly towards 0, right? So this one is the logistic regression error. Is that clear? Now, first of all, when we did logistic regression, let's quickly talk about logistic regression once again. Okay, so when we did logistic regression, we talked about t is equal to 0 and 1, right? However, like with perceptron and SVMs, like we are doing t's plus 1 and minus 1, right? So now how do I switch logistic regression from t is equal to 0, 1 to t is equal to minus 1, 1? Because that is what this graph is. Okay, it's kind of simple. Like, so you can just say probability of t is equal to 1 given y to be sigma of y, and probability of t is equal to minus 1 given y to be 1 minus sigma of y. Okay, so this is where one of the properties of sigma comes into play. So 1 minus sigma of y is actually just sigma of minus y. Okay, now I can have a compact notation, like, once again. So probability of t given y is given by sigma of yt. Okay, when t is equal to 1, it is sigma of y. When t is equal to minus 1, it is 1 minus sigma of y. Is that clear? So now I can construct the negative log likelihood. So the NLL is given by minus ln probability of the data set, which is basically minus ln product over n is equal to 1 to capital N, sigma of t of n, y of n. Okay, so this is nothing but minus summation over n is equal to 1 to capital N, ln 1 by 1 plus e power minus t of n, y of n. Okay, or in other words, summation over n is equal to 1 to capital N, ln 1 plus x of minus t of n, y of n. Okay, so with this, I added a L2 regularizer and normalized things so that instead of passing through 0, it passes through 1. Okay, like, more details are in the note, like in the notes. Okay, now we have seen many loss functions so far, right? Now what is the real goal of classification? Like, is it to minimize hinge loss or to minimize square error? Like, so what is the true goal? Like when we, like, what do we really care about classification? Like when we want to solve classification problems? Yeah. Having a perfect guess, like, which means you care about the misclassification error or the 0-1 error more than any other errors, right? Like, so our goal is really to minimize the misclassification error. Okay. Then why do we end up with trying other loss functions? So can you look at this graph and tell me like why it should be the case? Yeah.
Sometimes the model is not complex to have a perfect guess whatsoever.
Well, the answer, maybe I'll rephrase the answer. The answer is your model is not perfect, so sometimes it's okay to accept an imperfect model, but that doesn't have anything to do with the loss function choice, right? So I want to minimize misclassification error. However, when I do SVM, I minimize hinge loss. When I do logistic regression, I minimize logistic regression loss. When I do least square, I minimize square error, right? So why am I doing this? So if you remember our discussion during perceptron, 0-1 loss function is one of the most difficult loss function to optimize, okay, because it is not continuous. Okay, it's like a step function, okay? So it's going to give you 0 gradient almost everywhere, right? So it's going to be extremely challenging to minimize 0-1 loss directly, okay? So that is why we have all these continuous relaxations of 0-1 loss function, okay? Now you can see that in some sense, like you take all these loss functions, they start with a high value in the wrong side and the value reduces, right? Like, so it reduces monotonically. So in some sense, it approximates the step function, but in a very smooth way. However, you can also see from this graph why least square is a bad loss or classification, right? Like, so because the problem with least square is even if you are in the right side, least square is penalizing you. On the other hand, an ideal like loss function, like an ideal like approximation for 0-1 loss should be monotonically decreasing, like SVM loss or logistic regression loss. Is that clear? Also, the other observation here is you can see that the logistic regression loss looks very similar to hinge loss. However, hinge loss is flat, right? So, which means that you can actually get sparse solutions like support vectors when you use hinge loss instead of logistic regression loss. If you use logistic regression loss, like you will not set anything to 0. So like it's like you are going to use everything. So it's not sparse. Is that clear? Okay. So finally, like I think I want to introduce one more class of machine learning algorithms. Okay. So now that we have already seen a couple of examples of that, which is the idea of non-parametric methods. Okay. So in this course, we see a lot of parametric methods, right? Like, so when I say a method is parametric, it means there is a parameter, theta or W, that I'm trying to optimize. So once I find the parameter, then I can throw the example away and just use the parameters to predict the next prediction, right? Like, so in other words, parametric methods integrate all the knowledge to the parameter and use that to make prediction. Okay. However, there is an alternate class of methods called non-parametric. Okay. Now, when I say non-parametric methods, it doesn't mean they don't have parameters at all. Okay. The name is a misnomer. Like, so it just means it has infinite number of parameters in theory. Okay. Now, here is the difference. So, parametric methods and non-parametric methods. So in the case of parametric methods, you have a finite number of parameters. Like for example, if you do logistic regression with 100 features, you have 101 parameters. That's it. Like 100 features plus one bias, right? On the other hand, with non-parametric methods, you have infinite number of parameters. Okay. So why do I say infinite? Because in parametric methods, the number of parameters is independent of data set. However, in non-parametric methods, the number of parameters is dependent on data sets. It will become more clear once we see some examples. Like, so for example, in the case of parametric methods, we have logistic regression, right? GDA, the primal view of the SVM, right? Now, for non-parametric methods, if you think about the dual view of SVM, so the dual view did not have W in it. Instead, it just stored a bunch of examples as support vectors, right? So SVM, the dual SVM, the parameters in dual SVM are just the support vectors. You give me a bunch of support vectors, now I can make predictions. So have we seen any other non-parametric methods like that? Yeah. K nearest neighbors, right? Like if you think about K nearest neighbors, how you implemented K nearest neighbor in your assignment, there is no parameter that you're learning from KNN. Like KNN is like a very lazy classifier, okay? At least support vector machine is smart. It picks a very small set of vectors to store. KNN is extremely lazy in the sense it just saves all the examples. Like so you save all the examples and all the time you use all the examples to make prediction. That is one reason why KNN is slow, right? So like KNN. Is that clear? Okay, so I think we are moving more and more towards nonlinear models. Okay, so next week we are going to talk about decision trees, which are also nonlinear, which is like nonlinear like KNN. Okay, so we are going to see decision trees, and after that we are going to see neural networks, which are another class of nonlinear models. So before we jump to nonlinear models, right? Like so, I want to remind very quickly the notion of basis functions that we have seen so far, right? Like so, power of basis functions. So the beauty of basis functions is I can take any linear model or a generalized linear model, okay, and use nonlinear basis function to get nonlinear decision boundary. Okay, so I have a system which has a bunch of parameters, and you send some input X, and you make some predictions Y, right? In general, this is a linear system. Now, there are two ways to make this thing nonlinear. One, you just add a phi of X, so you send nonlinear inputs to a linear system, so it becomes a linear system. Or you just make this system nonlinear, right? So far, we discussed the first class of nonlinearity, like where we're doing this, right? Now, of course, this has disadvantages. The disadvantages, I need to really tune, like I need to come up with right set of basis functions. Like, so you cannot throw arbitrary basis functions and then like expect good performance. You have to really handcraft these basis functions. So on the other hand, like the advantage with the second class of nonlinearity is you don't need to worry about handcrafting things anymore, right? Like so however, here is a logistic regression example. Okay, so in the left-hand side, you see the original data, like in the original feature space, X1, X2, okay? And I'm using a Gaussian basis function here, like so one centered around here. So one centered around here and one centered around here, okay? There are two Gaussian basis functions. Now, in the right-hand side, you see the transformation. This is transformed data in Phi1, Phi2 space. Okay, so Phi1 is my first Gaussian basis function. Phi2 is the second Gaussian basis function. Now I do this Gaussian basis function transformation and just do logistic regression, which is like a generalized linear model, right? Like, so it can only learn a line, right? However, the advantage here is I'm learning a line on a transformed space, right? It so happens that for this particular transformation, I was very careful. I found these two right set of Gaussian basis functions so that in the transformed space, the data is linearly separable, even though it was not linearly separable in the original space, right? Now, if I take this line and apply the inverse of my basis function, okay, then you will get the circle in the original space. So the line in Gaussian basis space becomes a circle in my original space. Like, or in other words, I get a nonlinear decision boundary in a very cheap way, right? Like, I did not worry too much about nonlinearity. Like, I just added a bunch of basis functions and I got nonlinear functions. So, but moving forward, we will see other ways to make things nonlinear. Okay, so probably we will finish early today. So, but I'll take some questions now. So, are there any questions so far? So, had I known I will finish 10 minutes earlier, we could have taken a longer break. Yeah. Yes, that is the property of the duality. So, like when you have a dual formulation, like it has to satisfy KKT conditions. So, well, this is of course not an optimization course, like, but if you are curious about primal dual problems, duality, convex optimization, and stuff, well, you can find an optimization course in the math department. But I'm not sure if the website already lists Stephen Boyd's lecture. Does it? In the prerequisites? I'm not sure. If not, I will add it. Okay. So, like, there is a really great set of video lectures from Stephen Boyd from Stanford. In fact, he has two courses, Convex Optimization 1 and 2. And he has a textbook, which is a very standard reference for optimization. So if you are more interested in something like what we did today. But this is also very dense. Okay, so what we did is really dense. And I think I managed to abstract out the optimization as much as possible. But it is worth learning. Like, you should go back and read about it. Yeah.
So SVM with the kernel trick is an example of the first kind of nonlinearity.
Yes. Yes. Because with kernel trick, you still have to design kernels. So. Okay, are there any questions in the chat? Well, there are a lot of answers in the chat. That's good. Also, I think the exam dates are announced, right? So when is, did I mention this in this class or in the oral class? Like, somebody asked me about exam dates and I said, it's announced. I think for both the courses, the exam dates are announced by the university. So if you're someone not from Poly, like maybe ask in Piazza, somebody might be able to help you to find the exam dates. I will also ask the TAs to put the exam dates in the course website. Are there any, okay, so there is another question. So the question is, in this case, why did you not consider the decision boundary as two parallel lines? Well, it is not that trivial, right? So how would you model two parallel lines, like in an equation? Or how would you decide how many parallel lines to draw, right? So it's not, it's a good thought, but it's very non-trivial. Okay, any other questions? Yeah.
For this transformation, did you guess it by displaying the data on the graph? And if so,
okay, so that's a good question.
Yes.
Yeah. So this is a small, like this is a 2D example, right? Like I can actually guess, like where should I put my Gaussians on? But when you are in a high dimensional problem, like when you cannot visualize things, it is going to be impossible to guess, right? So one of the normal things that people do with basis functions is you take the data, you find the interval of the data points. Okay, so let's say there are like 10 variables, each in different intervals. You randomly sample points covering the entire space. So the hope is to generate as many basis functions as you can, so that together they actually cover the space. It's an art, so like it is difficult, but there should be a lot of heuristics available. Like for example, like let's consider even this, right? Like so, like for example, like let's say I cannot visualize this, but I know the range is from -1 to 1 and -1 to 1. Okay, then I can just decide to do 10 basis function randomly, like one here, one here, one here, one here, one here, one here. Like you cover the space, then you're going to have like somehow achieve what you want with careful tuning, of course. Well, maybe like there is another thing that I want to highlight, given that we have some time. So your third assignment is going to be using sklearn, and you will be solving a classification problem, like I think language, like NLP classification problem, by using different things like random for, like we haven't seen decision trees yet. We'll see tomorrow, like the next week. But you will be using SVMs and logistic regression and a bunch of other classifiers that we have seen so far, like naive Bayes. Okay. Now, the scope or the goal for the third assignment is really learning how to do hyperparameter tuning. Okay, because you are not going to implement the algorithms by yourself. Like so, you can use the algorithms from sklearn. So you're not going to implement SVM, you're not going to implement naive Bayes. Like so, you're going to use the ready-made algorithms, which means the majority of the work is going to be hyperparameter tuning. So, like the hope is you'll learn how to tune these models with practical packages by the end of the third assignment. Okay, so if there are no more questions, I will stop here. And it's my office hour for the next 1 hour, so you can come and ask me more questions. Thank you.